So let's look at this example. The process is sensitive only to clock. So only if there's a rising edge clock does the process turn on. Once the process turns on, we look to see if there's a clock transition, the process turns on. Once the process turns on, we check to see if it was a rising edge transition. If it was a 0 to 1 transition, then we look to see if the clear has been asserted. If the clear has been asserted, then the Q is equal to 0. If the clear has not been asserted, then Q is assigned the value of D. So as you can see this time, the operation of the clear is dependent on the rising edge of the clock. Only the clock can turn the process on, and only if there's been a rising edge of the clock will the clear be evaluated. So let's combine these two concepts together. Now we have a D flip-flop with an asynchronous clear and a clock enable. Since the clear again is asynchronous, it goes in the sensitivity list and we check for it before the rising edge. Since the clock enable is a synchronous control, it does not go in the sensitivity list and we nest it underneath, or we test it underneath the rising edge of the clock. So let's take a look at this code. If the clock or the clear are asserted, the process turns on and begins executing. If the clear is asserted, then the output is cleared, and that's all that happens. Only if the clear is not asserted do we check to see if there is a rising edge of the clock. If there is a rising edge of the clock, then we check to see if the enable is asserted. If the enable is asserted, then the Q is assigned the value of D. If the enable is not asserted, well, what happens? We don't have an else clause. What does the logic do if the enable is not asserted? Well, it does nothing. In this case, if the enable is not asserted, the register retains its previous value, which is the function of the enable. So the thing to remember is that signal assignments will automatically infer registers when you place them inside an if-then statement that checks for the clock condition. So looking at the example here shown in red, as you can see, there's an if rising edge clock statement, and then nested underneath there is the signal assignment Q gets the value of D. So that will generate a register or D flip-flop. If I had 5, 6, 7, 50, or 100 signal assignments listed underneath this statement Q gets the value of D, they would each generate registers individually. So let's expand that idea and look at the counter. A counter is essentially an accumulator, so it consists of a register and an adder. The register outputs a value, and that output value is fed back and added to some count value. So let's look at the code that we use to build this. In this case, the counter has an asynchronous reset, so there's a clock and a reset in the sensitivity list. If either one of those transition, the process turns on, checks to see if the reset is asserted. If the reset is asserted, then the temp Q value, which is a 16-bit standard logic vector, is driven to 0. Now this others clause here is another way to assign all the bits of the temp Q vector to 0. So you can see others 1, others Z, but in this case we're clearing out the temp Q vector. If the reset has not been asserted, then we check to see if there's a rising edge on the clock. If the rising edge on the clock, then temp Q gets the value of temp Q plus 1. So we're taking the previous value of temp Q, adding 1, and assigning it to itself. Then lastly, we assign the value of temp Q to the Q output of the counter. Again, the synthesis tool recognizes structure and builds the counter logic for it for me in hardware. The last topic I want to discuss in this training is the idea of designing hierarchy. If you're designing hierarchy and you want to include a lower level block into another VHDL model, then it requires doing two things: the component declaration and the component instantiation. Every lower level file or module that you want to include in a model must be declared and instantiated, but only the files that are directly included in that model. So for example, here in this diagram, I have two lowest level files, bottom A.VHD, bottom B.VHD. In mid A, I want to include or use the block bottom A. So that means that bottom A must be declared and instantiated inside of mid A. In mid B, I want to use both bottom A and bottom B. So in mid B, both bottom A and bottom B have to be declared and instantiated. Then in the top level file, the top level block, I want to use mid A and mid B. So that means both mid A and mid B must be declared and instantiated in top. But top has no concept of bottom A and bottom B. They're basically hidden by mid A and mid B. Only the blocks that you directly want to instantiate or include in that file need to be instantiated inside of it. This slide shows how to do a component declaration and instantiation. For a component declaration, you use the keyword component followed by the name of the lower level file you want to instantiate, followed by the keyword port. Then in parentheses, you list the name of the ports, colon, their direction, and their data type. You end your component declaration with the keyword end component. Many times, the easy way to do a component declaration is to just copy the entity declaration from the lower level block, paste it into your architecture declaration section, change entity to component, and get rid of the is. To do the component instantiation, this is where you want to map the lower level the ports of the lower level block to signals in the current level of the design. To do that, you want to assign a unique instance name to each instantiation of that component. Say for example, I have a lower level block and I want 5 copies of that block in my design, then I would provide a unique instance name to each copy. So to do the component instantiation, you specify the instance name, colon, and then the name of the lower level design block, the keyword port map, and then you map the lower level port name to a current level signal using the mapping character, which is the equal greater than signal. Each mapping is separated by a comma. So let's look at an example of this being done. We have an upper level block or an entity called toll EAB, and in toll EAB we're including a component called toll V. So again, we have to do two things: the component declaration and the component instantiation. So in yellow we have the component declaration. We're defining toll V and its ports, which include the input ports clock, cross, nickel, dime, and quarter, and the output ports green and red. Then down in the architecture body, we do the instantiation. With the instantiation, we call this an instance U1, colon, the name of the lower level block, toll V, and then the port mapping. We're mapping the clock signal in the lower level toll V to the signal T clock, which is an input in toll EAB. We're mapping the lower level signal cross, which is an input on toll V, to the upper level signal T cross, which is an input in toll EAB. Follow that same path. Nickel is mapped to T nickel, dime is mapped to T dime, quarter to T quarter, green to T green, and red to T red. Thus we mapped all of the lower level ports to signals on the upper level design. So that concludes our discussion of the VHDL basics. So from this training, we looked at how to use various VHDL design units and constructs to create a model. Examples of those include the entity, the architecture, signals, variables, and processes, both implied and explicit, as well as how to do logic synthesis and design hierarchically. This ends the recorded presentation. In order to improve future training material, the training department at Altera appreciates any feedback you can provide. After you register for this course, a confirmation email was sent to you containing a link to a short online survey. Please fill out the survey to let us know your thoughts on both the material and our method of delivery. Thank you.